Hey, Algebra 2, in this lesson, we're going to work to solve simple exponential equations. We're going to solve them by rewriting the expressions on each side of the equation as a power of the same base so that we can get the exponents. So we can sort of make the exponents their own equation so we can solve for it. It's pretty fun, and I hope you enjoy it. So first of all, work with your partner or group. We don't have either, so just look at these. See what you think. What would x be? First one's pretty simple. If you have the same base of 2, your exponents are going to be the same, so x is going to be 3. If you have the same base of 2, your exponents are going to be the same. We don't have to write a power of 1, so x is going to be equal to 1. Here, you don't have the same base, so 2 to the x is equal to, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 to the 4th power, so x equals 4. A few more. Not very easy to solve it when it's a subtraction, but we can change this into an equality. 2 to the x equals 64. So we have 2 to the x equals, let's see, I think we're at 2 to the 5th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. Yep, 2 to the 5th power, so x equals 5. Here, again, we're going to go 2 to the x equals 1, just move the 1 to the other side. And here you have to remember, anything raised to the 0 power equals 1. So x equals 0 in this case. Alright, little fun here. We have 2 to the 3x, and we just said 64 is 2 to the 5th. So we're going to take the powers and set them equal to each other. So x equals 5/3. Okay, 2 to the x plus 1. Here we have 2 to the 4th power. So we set the exponents equal to each other. X equals 3. Cool. So that was sort of fun, wasn't it? I don't know, I enjoyed it. We're getting into a part of Algebra 2 that I think is a lot of fun, so I hope you agree. So when we have both sides of an equation written as the same base, we did a base of 2, we can always say that the exponents are equal to each other, right, every time. But it has to be the same base. If I have 2 to the x power equals 10, I can't get 10 into the same base. Okay, it's nothing that I can do. So I wanted to point that out. Let's see. Here, I know that x can be in between two numbers. Like 2 to the 3rd power is 8, and 2 to the 4th power is 16. So x is somewhere between 8 and 16 to get to 10. Okay. What we are actually going to do, let's see, we're actually going to sort of squeeze these exponents closer and closer together until we can get pretty darn close to 10. Alright, so let's try. The Escherichia coli bacteria, commonly known as E. coli, let's call it that from now on, reproduces once every 30 minutes, meaning that a colony of E. coli can double every half hour. Mycobacterium tuberculosis has a generation time in the range of 12 to 16 hours. Researchers have found evidence that suggests certain bacteria populations living deep below the surface of the earth may grow at extremely slow rates, reproducing once every several thousand years. With this variation in bacterial growth rates, it is reasonable that we assume a 24-hour reproduction time for a hypothetical bacteria colony in this example. Suppose we have a bacteria colony that starts with one bacterium and the population of bacteria doubles every day. What function p can we use to model the bacteria population on day t? We do these models all the time in Algebra 1. We've got our initial value of 1. So p of t, our initial value is 1, and we're doubling each day, okay? You don't need to write the 1 there, but I just wanted to, it's a pattern that we've learned in Algebra 1. Time has to be greater than or equal to 0. So let's go ahead and fill in the table. Just for days, I've got 1, 2, 3, 4, 5. Okay, 2 to the first power, 2 squared, third power, fourth power, fifth power. Did I make a mistake in the last video? Or the last slide? No, 2 to the 6th power is 64. I didn't say fifth power then, did I? Well, I'm not sure. Alright, we're going to use this, so make sure you fill in your table, okay? How many days will it take for the bacteria population to reach 8? It'll actually take 3 days because p evaluated at 3 is 2 to the 3rd power is 8. How many days will it take for the bacteria population to reach 16? Looking at the table, that's 4 days, because p evaluated at 4, 2 to the 4th power equals 16. Roughly how long will it take for the population to reach 10? Well, we don't know. It's somewhere between 3 and 4 days, because 8 is too small and 16 is too big. So between 3 and 4 days. So we have to find how many days to reach 10. We already know from our previous discussion that 2 to the d equals 10, then 3 is less than d is less than 4. And the table confirms this. At this point, we have an underestimate of 3 and an overestimate of 4. How can we find better over-under estimates for d? Well, we need to break it down into smaller numbers. So we take the smallest, the underestimate, and we add decimals. So 3.1, first we always go in the 10th column. And honestly, when I worked through the problem set, I sort of started with the middle to see where I was, and then I went up or down from there. I didn't always start at 3.1. Now I need my handy-dandy calculator. So 2 raised to the 3.1. 8 points, and we're going to do 3 numbers after the decimal place. 8.574. Keep going, 9.190. We're looking for when it tips over 10. 9.849, we're still under 10. 10.556, so we actually don't need to do 3.5. Okay, right here is where it's our tipping point, right? So we're actually going to grab the smaller one and start messing with it. And how do we mess with it? So from our table, we now know another set of over-under estimates for the number d that we seek. What are they? Continue the process of squeezing the number d in between 2 numbers until you're confident you know the value d to 2 decimal places. So we just said it tipped over at 3.4, so we're going to take 3.3. So 3.31, 3.32. And you'll get used to this as you work through the problem set. Like I said, I always went for the middle. Like this is where I started, and then I would go up or down from there. But let's do it. 3.31, sorry, 2 raised to the 3.31. I get 9.918. And then 9.987. and then 10.056. So there we are, our tipping point. So we're going to take this number and squeeze a little bit more, right? 3.32. So we'll start at 3.321, 3.322, etc. See how we're just taking another space after the decimal and increasing that by 1. So all of the 3's are the same, we're just increasing the 100th spot by 1, and then the 100th spots are the same, we're increasing the thousandth spot by 1. So 2 raised to the 3.321 is 9 point, we know we're close, 994 and 10.001. Okay, pretty darn close. So we've got 3.321 is less than D is less than 3.322. Both numbers round to 3.322. 3.32, sorry, both numbers round to 3.32. So we can say D is approximately 3.32. So the population reaches 10 after 3.32 days. So 2 to the 3.32 is approximately, let's see, 2 raised to the 3.32, 9.987. Pretty darn close. What if we wanted to find D to 5 decimal places? Well, we'd have to keep squeezing our over under until the first 5 decimal places agree. Okay, so we just have to keep on going. To the nearest minute, when does the population of bacterium become 10? So we said 3.322 days on our table. I know you can use 3.32, but this would be 3 days. I have 0.322 times 24 hours, 7 hours. So I did 0.322 times 24, and I got 7.728. So now I'm going to do 0.728 times 60. And that gives me 43.68 minutes. So 3 days, 7 hours, and 43 minutes. I'm going to go ahead and round down. I know it's a 6, but if I go up to 7, we may be over 10. Alright, could we actually repeat the same process to find the time required for the bacterium population to reach 20? That'd be 2 to the D equals 20, or 100? Okay? I mean, we could do this for everything. If we were going to do 20, let's see, I had 2 to the 4th power equals 16, right? And then 2 to the 5th power is 32. So I'd be squeezing in between these two numbers. Okay? I'm not going to do it, but we could continue to repeat the process and eventually squeeze the solution to the right time, to the right days. Okay? Alright, So use the method from the example to approximate the solution to the equations below to 2 decimal places. Okay? Okay, we're just going to do 2 of these. If we were in a classroom setting, I would group you up into groups of, I don't know, 2 students and split this work up so that we could all practice and get back together and check our work. But let's just go ahead and do 2 of these. Actually, let's not do 4. Let's do 5. Let's see, 5 to the 4th power, 5 to the 5th power, I'm just guessing, yep. 5 to the 4th power is 625, 5 to the 5th power is 3125. That's a 2. 25. So it's somewhere in between them. So let's just do these 2. Okay, and I'm going to get a separate sheet of paper, or a separate slide. You know, sheet of paper. So we're doing 2 to the x equals 1,000. And we said that x is in between 9 and 10. So we're going to make a table, x and 2 to the x. So we'll start out with 9. And like I said before, I usually start in the middle. I know it's silly. But I start with 9.5, 2 to the 9.5, and I work my way up or down. So I have 724, 077, 2 to the 9.6, 776, 047, 8, 31, 746. This is when I get nervous though. I'm like, oh no, did I make a mistake? Ooh, 2 to the 9.8. I raised 9 to the 9.8. And you can even skip, I mean, you could have skipped from 0.5 to 0.7 and sort of do a little bit of jumping around. If you keep everything written down, keep your paper organized. Well, at 9.9, I'm at 955.426, and we did 2 to the 10, which gave me 1024. So that's our tipping point, so we're going to grab this number and keep going. So I have x and 2 to the x. I'm at 9.9, so I'm going to do 9.95 because that's just how I am. I have 989.12. Well, I've been doing 3 decimal places, let's keep with it. And then 2 to the 9.96 is 9, getting close, 995.999. 2 to the 9.97 is 1002.926. So my answer is, the closest will be that. We're in between, well, if we want 2 decimal places, I need to go one more, because I have to round. So let's do it, x and 2 to the x. So this is what I'm going to go with. I'm going to keep on going. 9.96, I'm going for the 5. 2 to the 9.965. Ooh, 999.456. 2 to the 9.966. Haha! 9.966 gave me 1000.15. So that is where I am. Therefore, my answer, if I'm rounding to the 100th spot, would be x equals 9.97. Cool? And really, this should be approximately. Okay, let's try the other one. I think I did 5, yeah. Okay. So we did 5 to the x equals 1,000. I don't remember what I said that was. So 5 to the 4th equals 625, and 5 to the 5th equals 3125. So let's try it. X, 5 to the x. I'm pretty sure starting in the middle might not be a good idea for this one, but we're somewhere between 4 and 5. So let's just start with 4.1, 4.2, 4.3, and see how it goes. 5 to the 4.1, it's already going up pretty fast. Those exponential functions, I tell you. 5 to the 4.2, 862.331. 5 to the 4.3, ooh, tipping point, 1012.910. So I'm going to go with this number and go again. X and 5 to the x. 4 point, well, I'm going to start in the middle again. So 4.25, 5. 5 to the 4.25, 4.25, I typed in the wrong thing, is 934. Okay, we're good. 593. 5 to the 4.26. 949.756. 4.27 is 965.166. Was this fun watching me do math? 4.28 is 980. We're almost there. 825. That should be an 8. 5 to the 4.29 is 996.739. We already know what 4.3 is. So we're going to stick with that 4.29 and go one more time. X, 5 to the x. 4.29, I don't know, 3. 5 to the 4.293. There's no right where to start. I mean, you can guess and go up or down if you've overestimated. Like right there, I'm over, so I know I need to go down one more. 5 raised to the 4.292. 999.952. Okay, so that's where we are. X is between 4.292 and 4.293, which both round to 4.29. So X is approximately 4.29. Cool? All right. So, something that we're learning. If we did a bunch of these, let's see, let me get a new slide. What we could have learned, I'm just going to give you a little summary, a pattern to the solutions. The larger the base, so our bases go from 2 to 16 in this problem, and we did 2 and 5. I probably should have picked a higher number. So the larger the base, the smaller the solution. That's smaller. Let's rewrite that. The smaller the exponent. Oh, for goodness sakes. Okay. So the larger the base, the smaller the exponent, because the exponent needs to be smaller to get to our goal of 1,000. Okay, that's really it. Oh, that's the rest of them. We're not going to do that though. Okay, let's do our problem set next. I thought it was a lot of fun, so I hope you enjoy.